Welcome back to Notes for Chapter 9. You have reached the finale of the semester, and we are now going to be talking about comparing two samples to each other. So let's discuss independent and dependent sampling. Independent sampling is when the individuals selected for one sample do not dictate or have a relationship with the individuals in the second sample. Dependent sampling, a lot of times, is called matched pair samples. This is when the individuals selected to be in one sample are used to determine the individuals in the second sample. Sometimes it's the same individuals, like Mrs. Main deciding to work out. So I'm going to weigh myself before I work out, and then I'm going to weigh myself after working out. So that would be me compared to myself. Another type of dependent sampling could also be spouses. If you directly pair a spouse to their spouse. So like if you compare myself, how much time I talk when I'm at home versus how much time my husband talks when he's at home. So we're comparing each other. Or you might do twins compared to each other. That would also be a matched pair. Let's look at a couple examples. It says, decide whether the sampling method is independent or dependent, and then determine whether the response variable is qualitative or quantitative. So remember, qualitative would be proportions and quantitative would be means. We've been talking about this all semester. So we conducted a survey of 100 random men and 100 random women to find out which was their favorite Olympic sport to watch on TV. So they are not, the men do not determine what women we choose. They were completely random samples. So these are independent of each other. And this would be considered qualitative because we're just asking them which sport. And so that means we're working with proportions. B, we conduct a poll of 100 random men and 100 random women to find out whether they like watching the Olympics on TV or not. We first call them the day before the games start, and then we conduct a follow-up call the day after the Olympics end. Okay, this would now be considered dependent because it is the same sample measured twice, a before and after. So you can think of the dependent sampling as same sample measured twice. Not always, but that's one way you can think about it. So this was a before and after, and again, it's a qualitative question. Letter C, a researcher wants to know if basketball or soccer players weigh more. A random sample of male college basketball players and a random sample of male college soccer players were obtained and weighed. Then their results are compared. So weight is something measurable. That's going to be quantitative. And so we're talking about means. And these are considered independent because they're basketball players versus soccer players. We also collected data showing the heart rate for a random sample of coffee drinkers before they drank coffee and also 15 minutes afterward. Okay, so it's another before and after. So these are dependent. And this is quantitative because they're measuring heart rate. Okay. We are skipping chapter 9.2. We're going to 9.3. And this is testing the difference between two means of independent samples with unknown standard deviation. So we're using a t-test. Okay. So let's look at our examples here. It says a study wished to compare traditional acupuncture with usual clinical care for a certain type of lower back pain. The 241 subjects suffering from persistent nonspecific lower back pain were randomly assigned to receive either traditional acupuncture or the usual clinical care. The results were measured after 12 months of treatments. These would be considered independent samples because they didn't receive both treatments. They received either the traditional acupuncture or the usual clinical care. And this is a measured pain level, so this is quantitative. They measure the pain level. We want to test whether there is a difference in the body temperature of men and women. We collect a random sample of 65 men and 65 women and take their temperatures. So temperatures are measured. So it's quantitative again. And the women and men are independent of one another. That's a new thing that we have to make clear in this chapter is how the samples are related to each other. They're not wives, they're not siblings or anything like that. Let's look at C. It says a recently published article reported the results of an experiment on reducing the percentage of men who develop prostate cancer. The investigators randomly assigned 3,305 men to receive the drug dutasteride and assigned 3,424 men to receive a placebo. Of those that received the drug, 659 developed prostate cancer. Of those that received the placebo, 858 developed prostate cancer. Okay, so we're really looking at just comparing the two samples, and one received the placebo and one group received the drug. So they are independent samples. And this would be considered qualitative because the question is really just a yes or a no question. And so they're going to find a proportion of the yeses. Okay. So both of these situations up here where it's independent and quantitative, this is what we would be doing in this lesson here. So let's look at example 2. Example 2 is giving us an opportunity to check out what it's like when we see printouts from a computer system that you might use if you're taking a psychology course or a business course or a sociology course. We don't use them here in this course that much, but I try to bring them in a little bit. So it says many baseball fans hold that because of the designated hitter rule, there are more runs scored in the American League than in the National League. A researcher for ESPN gathers data on the number of runs scored per game on a random sample of American League teams and a random sample of National League teams. So they're two different leagues, and so that's how we know they're independent. Okay. So they want us to verify that our requirements are met to be able to run a hypothesis. So in this chapter, we have our regular random sample requirement that we had before. And that's true. We have 2 random samples. Our second thing is they're independent of each other. And then our third thing is the independence rule. So the 20 times sample 1 has to be bigger, has to be less than the population, and then 20 times sample 2 also has to be less than the population. So 20 times sample 1, we can see they said there were 6 here. So there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 20 times 6 is 120, and yes, there is more than that in the sample, more than that players. And then 20 times 6 is 120, and yes, that is also less than the population of players. And then the fourth thing is the norm. We're checking for normality. And because we have small sample size, and they're both less than 30, then we have to use the normal plot. So the normal plots are linear. So we can say they are normal. So these are the four things that we've been using, but I just want to kind of bring them up again. Okay, the hypothesis test outputs for two computer programs are below. Use these results to answer the question. And so we have the mean of the American League and the mean of the National League, and then we're testing for a difference. So I'm going to show you two different outputs. There's the stat crunch output over here and the Minitab output. So when we're looking at two population means with unknown standard deviations, we are going to have a hypothesis statement of either the means are equal to each other. Let's look at that page. So looking at this page in the formula packet that is available for you to print on the website in Canvas in the modules. I'm going to put it in various places, but it's going to be in the getting started module as well, but I'm going to put it down also by the final exam module, which would be like module 15 or 16. So you can print it there, but it's what contains, you'll see kind of outlines for all of the hypothesis testing and confidence intervals and sample sizes that we're doing. So this one is for 9.3. And here again are the requirements that we're using. And here are the steps of deciding what hypothesis we're testing. So you can see here in this output, they have that mean 1 is minus mean 2 is greater than or equal to 0. If you add mu2 to both sides, you actually get this. So mean 1 is greater than mean 2. So we're talking about a right-tailed test. Mean 1 is greater than mean 2. So there's just a couple of different ways that they can be written. We've been learning about the p-value. So there's our p-value. There's our test statistic. When there's two samples, the degrees of freedom are calculated. We are not going to have to worry about calculating that by hand. And then our mini tabs print out here. It's going to be a little bit different as far as their degrees of freedom is exactly 9 that they use. Their p-value is very close to what the other one was. It's just rounded, but it won't affect the outcome. So it says how many American League teams were sampled. And there were 6. What was the mean RPG for the American League teams? And that was 5.185. You can see that here, American League, the mean. What was the standard deviation for the American League? That was 0.339. This is everything for the American League here. What does StatCrunch state as the degrees of freedom? So going back to the stat crunch, the degrees of freedom is 9.96. Rounded, it would be about 9.97. What does the mini-tab state as the degrees of freedom? They state 9. Like I said, they won't be equal. And what was the average RPG difference? So the average difference is 0.253. Right here is the average difference. So if you actually subtracted them, that's what you would get. State the test statistic. So the test statistic is here, which is 1.33. The T0 is 1.33. And the test statistic is here on the stat chart. And then it says state the p-value, box it on each output. So here is the p-value. Down here is 0.1066. And up here, it's right here. And there it's 0.108. So either way, it's going to give us the same result. It says use the computer output to perform step 4. And so remember that step 4 is the picture. And because it's a right-tailed, then this is what our picture is going to look for, a right-tailed. Remember the classical approach is that danger zone. So this is the danger zone. And then the p-value approach is just comparing it to the alpha. So this is our step 4 for the classical approach and step 4 for the p-value and the p-value approach. So we are going to just shade this, and our p-value is here. And our T0 is here, which is the 1.33. And so if the researcher set alpha at 0.05, would the results be statistically significant? So remember that we compare our p-value on the left to our alpha on the right. And our p-value is 0.1066, which is greater than. So we do not reject H0. And so if the researcher did use alpha at 0.05, what conclusion could be reached? And we, there is not sufficient evidence to support the claim that, going back to the claim, they're claiming that the American League has more runs than the National. Runs per game and National. So if the decision made above is incorrect, what type of error would you be making? And so if that were to happen, that is, we do not reject H0, but H0 is false, that would be a type 2. We do not reject H0, but H0 is false. Look at example 3. A study is done to determine if Company A retains its workers longer than Company B. Company A samples 15 workers and their average time with the company is 5 years with a standard deviation of 1.2. Company B samples 20 workers, and their average time with the company is 4.5 years with a standard deviation of 0.8. The populations are normally distributed. Are the population standard deviations known? No. So we use the t distribution. We're not going to be using the z at all in our class, but I'm just reminding you of why. So it says, conduct an appropriate hypothesis test at the 5% significance level. What is your conclusion? So we have our first step. And then in our formula packet, I've labeled out all the steps for you so you can have it handy. So step 1 is our hypothesis. And mean 1 is equal to mean 2. So remember, there's no numbers in these hypotheses. It's just comparing the two samples. And so I'm going to call them A and B because our companies are A and B. That'll be easier to keep them straight. And so they want to see if A retains theirs longer than B. So that would be a greater than symbol. So that's a right-tailed, and so we're going to do everything right-tailed just like we did on the last example. Okay, so my alpha, they said was 0.05. And then our test statistic, we're going to get from the program. So you're going to use the program in Desmos. And that program is right here. It's called two independent means. So it's two independent means. And so you're going to add in your sample size. So sample size there for A was 15. And the mean for sample A was 5. Standard deviation for sample A was 0.2. Sample size for B was 20. Mean for sample for company B was 4.5, and the standard deviation was 0.8. And then we're going to go down and we're going to leave this as 0 because that's what we're always testing against, that we're testing that the difference is 0 between them. And our alpha in this case is 0.05. And then we're just going to go down and click on the drop-down menu that's for us, which is this one right here, the right-tailed. And it looks like our p-value is, so step 5 is where we use the p-value, but let's write it down at 0.092. And I meant to grab our critical t. And this one, our critical t is at the bottom. So our critical t is down here. It's 1.3975. And I am going to save this. I'm going to make a copy and save this for you so that you can see that this is example 3 for 9.3. There's our test statistic. There's our p-value compared to alpha at 0.05. It's greater than. So we will not be rejecting a 0. We're going to draw a picture again, just like we did in the last one. And our p-value is right here. And so we do not reject H0. And so there is not sufficient evidence to support claim that company A retains workers any longer than company B. We have no evidence. Example 4 says, a study is done by a community group in 2 neighboring colleges to determine which one graduates students with more math classes. College A samples 11 graduates. Their average is 4 math classes with a standard deviation of 1.5. College B samples 9 graduates. Their average is 3.5 math classes with a standard deviation of 1 math class. The community group believes that a student who graduates from College A has taken more math classes on average. Both populations have a normal distribution. Test at a 1% level. Answer the following questions. Is this a test of 2 means or 2 proportions? 2 means, that we talked about an average and standard deviation. Are the population standard deviations known or unknown? So their population standard deviations are unknown. And so we're using the T, and we're going to complete our hypothesis test. So again, they're thinking College A is more than College B. So we're going to be doing a right-tailed again. So it's mean of A equals mean of B, and they're proposing that mean of A is greater than mean of B. Now, they won't always be this right-tailed. This happens to be the examples that I chose. Our alpha is different this time. It's at a 1%. So alpha is 0.01. And so we're going to go to the program and get our test statistic. But we can kind of draw our picture here. And then we can get ready to compare our p-values to our alpha, which is 0.01 this time. And before I put everything into the program, I'm going to kind of label it up here. So A has a sample mean. It has actually a sample size of 11, sample mean of 4, and standard deviation of 1.5. And B had a sample of 9, a sample mean of 3.5, and a sample standard deviation of 1. So it's good to kind of have that all organized so that when you go to the program to put it all in, it's handy. Okay, so I'm going to share my screen for that. Up here, we're just going to change this out. So it's 11, 4, 1.5, and then 9, and 2.5, and 1. Alpha this time is 0.01, and again, we're doing a right-tailed. So our test statistic, remember on this one, it's all the way at the bottom there. It's 0.8899, not very big. And so, but our p-value is still it's quite large. So 0.1997, 0.1997, which is definitely bigger than alpha. So once again, we do not reject H0. We do not reject age 0. So there is not sufficient evidence to say um, college A graduates take more math classes than college B. There you go. So catch me back for the next lesson on 9.4, and we'll see you soon.